Record on this computer. All right. So exam is out of your way. Don't expect me to grade it this week. I'm very, very busy. But the solution is on Harmon. So if you want to take chances and just ruin your weekend, you can do it. Otherwise, wait for me to grade it next week. So I had time to read through the what? The fishbowl. Yes, thank you. Very slow today. And so there are two different set of comments. So one is about the stuff from lecture. The other one is a general comments. If your comments, if your feedback is about we don't understand what the PA assignment is asking us, you should not put it there. You should ask me or put in Discord, see if anybody else has that problem. Here's the thing. When I write the assignment, I try to think it through the steps that is required, and then I design the question based on that. I try to give you resources. So usually in every PA assignment, there's resource about if you don't know how to code this or you don't know this method in MATLAB, for example, here's a good article to read. A lot of time you need to like a daily reading, right? So you go and read one thing and like, I don't know this thing, and you have to continue reading to learn. Some of you have experience, you don't have that, all right? Not all of you come with the same background, you're not even the same major, not the same year. So for me, it's always very difficult to design an assignment that fits everyone. I try to separate graduate from undergrad, but it's usually adding a little bit extra to the graduate student. The content is the same, all right? So, for example, for this PA assignment, I'm gonna go over, ask the question if you don't know. There is no stupid questions. If you don't want to, like, you don't feel comfortable raising your hand in front of your classmates, I created Discord for this. Just send a question and someone will answer. You only use Discord really close to the exam or homework when the homework is due, which increases my blood pressure because, oh my God, there's so many questions I need to answer. Like, no, that's not how it works. So thankfully there's no exam anymore, so I don't have to really best all the time. But it is for you as a resource, all right? So, if you didn't read this, please read right now. And tell me, what are your questions about PA assignment? PA3, programming assignment number 3. Okay, a lot of you are looking at me, so you already read, I'm assuming, all right? So again, this question seems familiar, right? So that's what I did in PA2. You had the question, the problem in your exam, so you started working. Where did you work on this problem? There's a class participation, right? And if you look at the book, it's the beginning of the chapter. It's literally solved. All you had to do was go to the book. Well, we didn't know, great, we had to go to the lecture. We didn't know, well, we needed to pay attention to something. Now you know. You usually get like I don't know, you lose maybe 1 or 2 points if you miss something in your checkpoint. So those are for making sure that you solve that problem. That is the problem you're going to be solving, and you already have all the equations. So that is the reason I put that CP for you. And this is the programming assignment based on that. So the math and theory part of it should be already solved, right? It comes down all to coding. You practice some animation simulation type thing in your previous assignment, so you should have an idea of how to do the coding part. Now, the part that you need to figure out is that, okay, I have some information. There is a video, right? Let's play it all together. I will play it. I need to make my 2-arm robot to do that motion. From the knowledge I have, what should I do? All right, it's up to you to figure that out, you and your teammate. Now, this time around, I will have another, like a checkpoint assignment, and I will ask you about your teammate's contribution. All right, because some of you leave the work for last minute, you don't carry your load, and it's impacting your teammates. and that's not acceptable. Either pick up the pace or be ready to be having a meeting with me about your performance. All right. So you basically are choosing a number of points that you want to draw on that donut, right? So your workspace is the donut, the circle in the middle, you don't reach. That was one of the questions in CP 14. Now, how many points you ask your user, right? So is there a golden number? No, but maybe like don't pick 2 points because there's so many curves that can go through 2 points. So you're fitting curves to number of points. I'll say 5, 6 is a good number. You don't also want 15 because then you're clicking, and every time you're running through this, you have to click on 15. At least for the first round that you're trying to figure out the code, do 4 or 5. And then if you needed to change it to some other number, then you can do it. So hard coded to 4 or 5, find out what's the solution, and then write the user input part. All right. Then what happens is that in your code, you have to first find a curve that fits through those points and is still in the workspace, right? Because your robot needs to be able to reach to it. Now, that's the tricky part because when you try the fitting at first, not all options are the way you expect. Some of the curve will go into the area that's not your workspace, it's not featured. All right, you need to tweak that curve fitting algorithm a little bit. All right, there's a little bit of digging. Once you've done that, and you know that okay, it works for every 5 points that I choose, then you can add everything and ask the user, like you put 5 or like 6 or 7 and see if this fits. If it doesn't, what should be your solution to make sure that the robot still stays in the same? Because your robot cannot physically reach to the white space in the middle and the outside, right? You have to set a limit to your user so they don't take those points, right? Or if they did, what is your solution for that? Remember, it's all critical thinking, like what my user can do and what should I do to help them, all right? There are a couple of options. I don't want to give away the answers, but I'm asking the good questions right now, things that you will face. Don't leave this for 2 days before the assignment because these are all the questions that you will get. Yes.
So what I'm trying to, of course, I know that potentially doing is a plane robot.
Yeah, it's a 2, yeah.
And
Our robot.
there, just having this robot arm from its home position,
Yes,
which is a starting point that they define.
yeah,
Having that follow a curve.
yes, I'm gonna show the video. That is going to be the same thing. Hopefully you can, like, if you look at Zoom again, you can see it. If not, you have access to the video anyway. So here they are picking the points and is drawing the line. This is very good because I can see where the points are. It fits the curve. Then this is your 2-hour robot. It starts from the initial point and track this line. Now, who's talking? If you remember, every line is made of points. You know the desired point that your end effector needs to reach at every single time. You choose what method to solve. I can't help you more than this. All right. Then solve first for the general simple case. Then once you figure that out, then try to think, okay, what are the other scenarios that can happen? What if the curve goes around in the white space that is not the white space? What can I do in my algorithm that the robot doesn't break? Continues on something and go back to it. All right. I've given you like 4 or 5 tips. It's recorded. So when you're doing the assignment, go back and listen to this part. All right. Okay. Now, with all of this, if you have questions, either ask me in my office hours or put in the Discord. If I see it, I'll answer if something that I think I can answer without giving you away the solution, or you can ask someone else, you know, it's part of the creative thinking. Don't look up the solution online. Again, this is for you to learn how to do this. This is line tracking. That's something that they do in robotics field. So you need to get challenged to learn this. All right. That was my spiel for the PA assignment. All right. Now with that, we're gonna go to our lecture today. Sorry, I didn't, do you have the link now? Do you have the lecture slides? Good. I uploaded it, but I didn't give you the link. So you have to kind of have access to that. Okay, so exam 1, you learn about kinematics, right? Exam 2, what did you learn about? Velocity kinematics and inverse kinematics, right? Now, one of the comments in Fishbowl was, we are not very sure why do we calculate velocity kinematic, and we're confused. What's the difference between forward kinematic and velocity kinematic? Can someone tell me what's the difference? When do we choose either one? Yes.
So forward kinematics would be when you have the forward variables you want to find
Position and orientation, right? So we are in position orientation. Now for velocity kinematic,
when you have the rate of change of the joint variables.
when you have the velocity of the joint variable and you want to find what?
The velocity
And the vector. So think about your car. You could have to find a problem. How far did I drive? How fast did I drive? How much time it took to get somewhere? Right? There's a position kind of problem, there's a velocity. So forward kinematic was taking care of the position, and you have orientation with the angles, and you have velocity. So that, but kinematic is about when we have information about the joint variables, we want to know where the end effector will end up. Now, inverse kinematic, what kind of problem inverse kinematic was? What's the inverse kinematic problem? No, what is inverse kinematic? What do we?
Oh, what it is? Oh, when you know the position you want to get to, but you want to know the changing angles that it takes.
You want to know the configuration of the robot that gets you to that desired position that you have, right? So that is your inverse kinematic problem. Now, we moved from all of that, so we finished all the kinematics. In kinematics, we didn't have mass, force, torque, anything. Now we are in dynamic. In dynamic, all of those fun stuff will come closer to the actual reality that you see. So we consider mass, inertia, force, momentum. We have on top of that all the joint variables and everything. The good thing about dynamic is that we have a generalized equation. We know how our equations look like. We just need to find the matrices and put it in there and then solve it. Solving it is ODE. You can use MATLAB or any other language to solve it for you. You don't have to do analytical anymore. All right. So finding those matrices are basically your job in dynamic. All right. So if you remember, we talked about Lagrangian. I told you can use Newton-Euler, but I introduced Lagrangian, and we're going to keep using that. All right, for developing our dynamic equation. So quick review, the kinetic energy is the work done to bring the system from rest to motion, right? To the current state that it is. We have two kinds of motion, linear and rotational motion when we are dealing with our robots, right? Now, if we have a linear motion, what is your kinetic energy? We show kinetic energy with K. 1/2 mv squared. V is linear velocity. If we had rotational motion, K is 1/2 I omega squared, and omega was theta dot, angular velocity. For a rigid body that is objected to rotational or angular motion to do, so this is when we usually talk about one mass, right? When we have rigid body, we usually have accumulation of like links are connected, and we show them with a mass. So in a rigid body, you could have different masses. Now, how do we write the linear and rotational kinetic energy for that? For the rotational, the equation is almost the same thing, but the way we write it is different because we need to perform matrix multiplication. That's the only difference. So K would be 1/2 omega transpose IC omega. IC is your tensor of inertia it's in matrix form. For kinetic energy of each link, so you could write that for the linear motion as well, right? So how would it look like for linear motion? 1/2 mi of that link, because that's a scalar, right? V transpose V. So you can actually multiply them. Yeah. 3/1 will be 1/1/3. So the total kinetic energy of a link I would be 1/2 mi. M is a scalar. VCI, the linear velocity of that link, times VCI plus 1/2 omega I transpose ICI omega I, because the inertia is a tensor, is a matrix, so it will be sandwiched in between the omega transpose and omega. You need to remember this, all right? Then your K would be sum of these KIs when I goes from 1 to N, and N is number of links. How many links you have, because you're gonna have that many masses. Yeah, so so you can use like a center of mass. Now, we don't remember tensor of inertia. Usually, if you have objects that are in the basic form, you can find them. If they're more complicated, you break them down into objects that are familiar and active. Now, for the purpose of this course, we'll only deal with very simple objects like rectangular or line or circle. We don't deal with complicated objects. But for in real life scenario, you actually have to find those. And sometimes it's not a linear or easy task to do. All right, so a quick review on Lagrangian and how do we convert our Lagrangian to and connect it to our equation of motion. So we introduced the equation of motion to be based on Lagrangian, that blue sentence here. If you remember, L was K minus U, kinetic minus and the negative potential energy. So if I replace that, if I substitute that in my equation here, I will get partial of K minus U, partial differential respect to Q dot, K minus U, respect to Q. Now, if we actually perform this and then simplify that, K Q dot minus U, partial of U, respect to Q dot, K Q plus U and Q. Now, if you look at this term, what's the value of this term for all kinetic energies? 0. Why? You don't have the Q dot in your kinetic energy, right? A potential energy, because it's either the gravity is mgh or is a spring system is 1/2 kx squared, so it's still q squared. So you don't have Q dot, so that term is 0. So this term is 0. Now we can simplify our Lagrangian to this form, and we directly have our kinetic energy and potential energy. So you're kind of going toward the general form of our dynamic equation. So these, and this is how is the external person force, right? So when you have a problem and you want to find the equation of motions, the equation of motion, what would be your process, your thought process to find that equation of motion, knowing that this is the equation you need to use? Is my question clear? Okay, so let's say you have a robot. I'll give you a robot, right? I give you mass, inertia, everything, and you know what kind of joint you have. And I say, write the equation of motion. What are the steps you need to do to get to the equation of motion? And I have to do programming. Does that make sense now? All right. What would be your thought process? How would you deal with that? That's your process. Mayhem, yeah.
So like, you first you create like an equation, or like, kinetic, and then you evolve it.
So you have to find out first how many links or well, how many joints you have, and there is one link in every joint, right? So how many links or joints you have, what kind of also, what is your generalized variable, joint variable is used, right? So you find that out, then you need to see what's the mass of your link, what's the potential inertia of the link, and then you have to write down kinetic energy for every single link, potential energy for every single link, and then which one is. You literally replace them here, and you will have your equation of motion. Doesn't matter what kind of robot you get. For so let me rephrase that. Manipulator. What kind of robot manipulator you get? This would be the process. Okay. Some are easier because if you imagine if you have only prismatic one, it's a lot easier than if you have prismatic and the loop. Right. So the process is the same, but like how much you write down is depending on the kind of robot you have. We are going to call this gravity vector, or because it's only depends on the gravity, or if it was moving potential. So we're gonna kind of address it, and the rest are the inertial forces. Because it's because of the motion of the system. All right. Now, do you remember we had this formula as generalized equation for our dynamic equation? So between this one and what you saw before, can we find terms that are equal to each other? So tau is tau, right? Tau was your generalized force and torque. What is QG if you compare with the previous equation? With this one? The gravity forces. Again, we are packaging it under gravity. What is Q? Generalized joint variable. All right, so what is M of Q? It's multiplied by Q double dot. Is a mass matrix. You will see it represent the kinetic energy. This is always symmetric and positive definite. For positive definite, I'm gonna add it to our next lecture, I think why positive definite and what is it. All right, but it has to do with the eigenvalue, all the eigenvalues have to be positive. Now we have this term, we either call them V or A. Do you remember what they were from before? These are quadratic term. What did they represent? So these are your quadratic terms. And there are two terms. There is first derivation in them, which if you have the product of first derivation, qi dot, for example, times q dot, qj dot, the two different joints, these are the Coriolis terms. If you have the product of qi squared, this one is centrifugal. How important it is for you to know which term is what? It is important because when you look at the model of the robot, what it does, you can check versus the equation you have and kind of sanity check, make sure that you have all the terms that is needed. Terms that should here are appearing in your equation. All right. So the rest is just finding out what goes into them. So we have the form of our equation. Example. That's it. That was the lecture. Now we're going to solve an example. I'm going to warn you, this is a little bit lengthy example. All right. At some point, I'm just going to have parentheses that there will be calculation in it, but you can't find all of those in the end. All right. I try to write them as much as I can. For the more lengthy one, can check lengthy. Okay. But I want you to look at this robot. This is what is this robot RP? So there is a revolution and there's prismatic, right? And you also asked me, can you write down the question? What is it that you're trying to find on each example? What am I trying to find? Equation of motion. Usually, if an example comes after a piece of lecture, that is the question. So find equation of motion of a RP manipulator with this information you have. You also have two more information. Let's say you know IC1 and IC2. IXX1, IYY1, IZZ1, and similar for the other one. So this just means, assume we have this. What is your approach? I want everyone to write their approach. How would you solve this? Step by step. That's all I want. No, Step one, are you trying to generalize what is the next? Nothing. Not in the math. What are the steps that you can take to solve it? That's our writing that right now. What is the step two? Find your Lagrangian, which is k minus u. I know I need to find my Lagrangian because I'm going to use the generous form for the equation of motion. Now to find Lagrangian, I need to find k, I, and ui. So the next thing would be find ki's, find, this is d missing here, ui. Once I found them, find sigma ki and sigma ui. Now I can create my L, then I can use E.o.M equation, which is this guy. So when I find KI's, I'm going to find and when I find this, I'm going to find this, right? So this is your approach. The rest is right, just doing the math. Are you still? I'm going to note that. But I'm gonna actually now solve it. I'm gonna follow my approach. I found Q is theta 1 and D2. So, well, we can say, well, we don't know what the prismatic is, but there is D2. You can say that we can assume the zero of the prismatic from here and then all the way there. Does it matter? Can I say no? It is like a D3 and it's going to be from the end effector plus a fixed value. You can also do that. Does that make sense what I'm trying to say? Because prismatic is either a fixed value added plus a variable, then you can use it separately or just put them all together. So just easily change. But there's always a fixed part into it. So just make the equation easier for myself there. Now I'm going to start writing, finding Ki and Ui's. K1, because I have two links, so I know I have K1 and K2. K1 is 1/2 M1 L1 squared theta dot 1 square. How did we do that? If you remember last or the example before, we got into this. You can write in X and Y direction, and then when you calculate both of them, you will get to L1 squared theta dot 1 square. So that's the linear part of it. Plus, we have the rotation because the revolute joint. 1/2 IZZ theta 1 dot. I'm solving it for one link at a time right now, so I can do that. Then this becomes 1/2 M1 L1 plus IZZ, and I can factor out theta 1 2, theta dot 1 2. K2 1/2 M2. Now this one is going to be this distance. D1 squared theta dot 1 squared plus 1/2 I ZZ2. So that one is ZZ1. Theta dot 1 squared plus 1/2 M2 D2 dot square. So what happened here? Can someone explain it to me? Why do I have two terms for linear velocity? Well, for kinematics, I have two kinematics terms, right? Why? Yeah. One, the rotation, one because of the kinematic. So, assuming that you remember all of this, so you are using your knowledge from before. Okay, it should carry. So D1, so you are separating, let me check, make sure that I'm saying right, but. It's D2. Yeah, I thought, I figured I was wrong. Yes, it's D2. Because it's the distance to the center of mass, but because of the rotation of the first drawing, there will be a linear velocity there. Thank you. Then the second part is the velocity that way. So you have two different vectors of velocities, right? One is pointing this way, one is pointing that way. Now we have K1 and K2, we put them together, right? That becomes your kinetic energy. So your K is K1 plus K2. I'm gonna write this one down 1/2 because you'll see how mass matrix will play in here. How about U? What is U1? What is U2? Right? So this is your gravity 1, the mass 2, mass 1, mg1, mg2. M1G L1 sine of theta 1. Then for this second one is M2GH2. Here is M2G D2 sine of theta 1. Now, because we counted this as D2, so we don't have to add them. But if you had it separately, simply just have to add to this, right? So it's nothing, not a big deal. I have to find U. So U would be U1 plus U2 is U. So it would be U becomes M1L1 plus M2D2 G sine of theta 1. This is U. This is K. So did this, so I'm gonna mark. Did this first part? Did this part right? Now, I kind of skipped the green part because I found this, but I still can't get the differentiation, right? It doesn't matter. I could do it separately and put them together or just put them together. So the next part that takes a lot of calculation is the partial differential part of it, partial derivative part of it, right? You have to do it for one by one per one. So for K Q dot I, right? And I also need to find D dt K Q dot I. I also need to find. So I'm putting down what I need to find. I'm following my steps. Then I also need to find
K with respect to Q. One more, U with respect to Q. Now let's see what they are. So since we have two links, these are all 2 by 1 vectors because they have 2 parts, K1 and K2. So partial derivative of K with respect to your first joint variable, dot 1. Partial derivative with respect to your second one, which is your D2 dot. Here you have similar, but with respect to your Q, so it's theta 1, and then this is with respect to D2. Here is U with respect to theta 1, and U with respect to D2. All right, so for first part, the partial derivative of K with respect to Q dot 1, you see that it's only this first sentence, right? So we can ignore that second one. So it would become whatever is in that parentheses there. Time Q dot 1. So 1/2 gets canceled with the 2. You have the coefficient times theta dot 1. For the second part, so for this one, you only have D2 here, and this becomes M2D dot 2. To find this sentence, you have to get the time derivative of this guy, which would be the same thing in the parentheses, theta double dot 1, and here M2 D double dot 2. For K with respect to Q, so what is partial derivative differential of K with respect to theta 1? Anybody listening, following? 0, right? You don't have any theta term. Theta 1 term there. That's 0. So the second part, if you have the first part all organized like what I did, the second part is a lot easier. So this is 0. What is a partial derivative of K with respect to D2? Huh? This one is a little bit tricky. Look at here. Right? So don't just look at all this D dot and then we don't have it too. So it is M2 D2 theta dot 1 squared. I'm going to change the color of this one so you can actually see what is happening. Oh, here. Last but not least, U term. So this is our U term. What's the partial differential of U with respect to theta 1? All of that parentheses times G times cosine of theta 1. And with respect to D2, we have this term here, right? So it would be M2 sine theta 1. Well, I'm going to put G here, and there is a reason for it, because G is a fixed number. So if you want to get it out, you could do that. All right, so we have 4 parts. Well, we needed 3 parts. This one, this one, this one to put in our equation of motion. We have all of them. We just put them back to back, equal to tau. Tau is tau 1 and tau 2, right? Because we have 2 links, we could have 2 external forces. So it might seem overwhelming and a lot, but if you follow the step, if you have that approach and follow one by one, what is the
how many equations you will need to remember to be able to write this? You have two equations for kinetic energy, one for potential energy, and the E.o.M. That's all you need to remember or have in your cheat sheet. And then just follow that depending on if you have prismatic or reverse. Right? So it is a lot to write, but the concept is not complicated. If you remember the approach properly. Now, if you put all of this together, you will get to, so you will have theta double dot 1, you have theta double dot 1 and d double dot 2. So when you open them, what would be the matrix that is multiplied by d double dot 1 and d double dot? You need to put it in matrix form after you put them all together, put in matrix. The coefficient of that is pre-multiplied by the rate of change of your velocity to the acceleration. What is it called? Mass matrix. That's how you find your mass matrix. So you need to put, after you just write them back to back, add in 3 parts. Then you have to write it in the generalized form, meaning that you have to put it in a matrix form so you can find your mass matrix. You can find your gravity forces, they're all multiplied by, there's a G in there, right? And multiplied by your joint variable, K1 and D, W1 and D there. And then everything else in between is Coriolis and centrifugal. You just put it in one matrix. So it has the quadratic terms of theta dot 1 times d dot 1, theta dot 1 squared. In the annotated version, I've done it, so I show you how to put it in matrix form. But you have to do that step because when you are coding in your programming, you write what is the mass matrix of this system? What is the gravitational force of this system? What are the Coriolis terms of this system? And then you say that follow this generalized form, define a function, and then you use one of the ODE methods. So the class participation is a very good example. It's simple. Simple meaning that it doesn't have a root join. Just this matter. So it should help you with understanding. I want you to write your approach, solve based on your approach, put together everything to the end. If you understand that approach is prismatic, the root is just going to be longer. Sounds good? Okay. Definitely do that because Friday's class is a little bit more math. We got to that part. Exactly.